Hi, everybody. My name's David Austin, and I am a senior principal AI engineer at Intel. I'm also a Kaggle Grandmaster. If you're not familiar with Kaggle, what that means is I spend way too much of my personal time working on AI competitions. And that's one of the things I'm here to talk to you about today. I am going to talk about how we could take a previous first place Kaggle solution and see if we can supercharge that using SigOpt to take us to even higher results than we initially got. So I'm excited to talk to you about this topic today. So first, let's talk a little bit about what the challenge was here. AI challenges are still very prevalent in the industry. They're really good at helping move the state of the art forward, getting lots of people to collaborate, compete, work on these challenges to see what we can learn about solving these problems, both at the individual and a global level. And the particular challenge that I'm going to talk to you about is there was a Iceberg Classifier challenge. Now, this challenge was launched about 3 years ago, and at the time, it was the most participated in ever image classification competition. So there was a lot of interest in this one. And what we're trying to do is classify ships versus icebergs using satellite imagery. The reason for doing this is aerial reconnaissance happens in different areas of the sea to see if we can determine if there's unsafe conditions that ships are traveling through, if there's hazards in the way, or if there's potentially other ships. So it's important to be able to distinguish between the two. Now, the reason why this challenge, I believe, is so interesting and why it was so well participated in across the industry is there are some unique features to it that bring us closer to some real world type scenarios that we have, especially in things like the industrial space where I tend to do my work. So number one, we're dealing with a small training data set. A lot of competitions have large amounts of data. If you're familiar with ImageNet, there can be thousands of classes, millions of images. Those bring their own challenges. But when you're talking about small data sets, you're talking about something that's more within reach of the compute capability of most people. You're talking about higher importance on a per image basis. And it's a lot more reflective of how we solve real problems in the real world. So there's only about 1,600 images across the two classes, and each one was only 75 by 75 pixels and 2-channel images. So these weren't RGB. Each of the two channels were different bands taken by radar backscatter, and there were horizontal and vertical polarizations to each one. Now, what really caught my attention here and why I thought I wanted to invest my own time working on this challenge was take a look at the images here on the screen and look at the ones that are labeled iceberg and look at the ones that are labeled ship. So when my eyes look at these images, what I see is it looks like a 1970s television with a bunch of snow in the background and a single dot in the center. There's not a lot that you can see here visually from a human perspective that gives you much insight into what's a ship and what's an iceberg. So as a data scientist, this is pretty intriguing. If I can't, there's a rule of thumb that I think a lot of us use is that if we can discriminate the differences between classes with our own eyes, well, then we should be able to train an AI system to do that. But when our own eyes can't see the difference, that becomes pretty interesting. So this was one of my first challenges that I worked on to really see what can AI do for me here. Because if this is reliant on a human to do this kind of classification, well, I think we have problems. So if AI can help us move that forward and solve this problem, great. I'm all in to help and work on that. So that's why I think this is a interesting problem and not your run of the mill cats versus dogs, relatively large class difference that we're trying to discriminate against. Okay, so if you're not familiar with the competition community in general, most of these competitions are hosted by someone, a host, the largest one of which is currently Kaggle. It's a platform for data scientists. They host dozens, if not hundreds of competitions in a given year where hosts will come in, provide data set, provide metrics, and then the data science community can either work together or work independently, have a platform to share information and work on these problems. The actual sponsor of the competition, who actually brought in the data, who was most interested in solving this problem and provided the prizes, was Statoil. So that's a Norwegian-based energy company. They're global. They're in 20 countries around the world, focused on energy exploration, and they deal with a lot of these ships that are traveling around the world and who run into these types of challenges. And so that's who actually hosted and brought this all together. Now, something that I think is important to understand when you're dealing with these types of well-defined, constrained problems and competitions is there are differences to the real world. And we have to be aware of that and acknowledge that, because it changes our approach to some of the problems. So the nice thing about competitions is you have a lot of things given to you, wrapped in a bow, that you can start working with as a data scientist that generally don't show up in the real world. Real world problems that I work on, generally, nobody's bringing me an entire data set that's fully labeled, fully validated, clear KPIs, understanding of how I'm going to trade off the complexity of the problem with simplicity, how I'm going to trade off accuracy versus the latency it needs to run on, right? That doesn't happen in the real world. A lot of that you have to do yourself, and this is a lot of the hard legwork. Now, this is one of the nice things about challenges and competitions is that is given to you. So in this case, you're given the data set. It's been validated. It's been labeled. There is a single metric to optimize for, and that is accuracy, or some version of accuracy. In this case, log loss, but you have a single metric that you're trying to optimize for. And as such, there's essentially no what I'll call real world or algorithmic constraints. If you want to have a ugly solution with hundreds of models that you're ensembling and stacking together, go for it. It's all about show us the art of the possible, show us how you can maximize the accuracy. Okay, so a little bit different than the real world, but the point here is on these types of challenges and where accuracy is king, that's the type of solution that you're going to get. And as you're going to see here, I'm going to walk you through what did the best solution look like for this 3 years ago that we developed versus what does it look like today? And more specifically, how could we bring that solution accuracy up even higher using SigOpt? So this is the winning solution architecture. I was fortunate to be on the winning team that developed this solution. I'm also looking back 3 years, quite astounded that this is the type of thing that was state of the art 3 years ago, given where we are today. So what the solution was here was a what I would consider by today's standards, very ugly, very unmanageable solution, but one that could deliver the highest accuracy based on the 3,500 solutions, where there were 181 all customized CNNs, every one of them customized with different layers, different convolution size. 181 of these that were trained, stacked together, ensembled, and then some final post-processing and prediction layers on top of this. Now, in the real world, you would not want to take, believe me, you would not want to take 181 different customized models and try to maintain it, sustain it, look for drift, do the types of things that you need to do today to productionize a model. But remember, that wasn't the purpose. The purpose was give me the best accuracy possible. So this is what we came up with. Now, just a little bit more detail here. So you can see this was what I would consider a really brute force random search solution versus some of the more elegant searches that we can do today to optimize. So, we varied everything from the convolutional layers, the amount of dropout by each layer, the filter size, the type of pooling, et cetera. So, and it was very brute force. So every iteration we'd go through, vary these parameters randomly. If we can make an improvement on val accuracy or val loss, great. We kept the model. If not, tossed it out. So doing that, and ultimately about with close to 200 of these models came to the winning solution and just incrementally improved accuracy. Very ugly, very brute force today. So natural question, as I've been using SigOpt for a lot of the real world problems that we work on, is, hey, if I were to take this first place solution from a few years ago, okay, do two things to it. Let's update it now with some of the more modern architectures and see, well, just by changing architecture, how much of a, I'll call it a free boost, could we get today? And then on top of that, run it through some of the optimization routines in SigOpt and say, hey, can I even beat what we had done a few years ago with this, very, elaborate, if not ugly solution? So let's take a look and see what we could do here. So a lot has changed in the world of AI in 3 years. We obviously have gone through a lot of different iterations of model architectures, from efficient nets to transformers and things like this. And so very, very much ahead of where we were a few years ago when things like inception, exception were state of the art. So first thing here, so because we were dealing with small images, only 2 channels, and adding a third channel, an artificial channel, just an average of the first 2 channels, so we can use architectures that are tuned for 2 channels, or sorry, for 3 channels. We used efficient net B0, okay, with an updated learning rate schedule, a little bit more modern, using 1 cycle learning rate. And only doing flip augmentation. So we're not adding a whole lot here from an augmentation standpoint, or throwing much more than just, let's just update the model architecture and re-baseline ourselves based on where we are today. So doing this would give us a little over 87% accuracy, which is really close to where we were with the first place solution originally. I think this is an important way to re-baseline ourselves, because we don't want to say, hey, we're going to do all this optimization on this ugly architecture. Let's really just take architecture out of the equation, re-baseline ourselves. Okay, now we're back up to really close to where the first place solution was just by updating the architecture. Now, what can we do on top of this to take it even further? So a little bit more background here on the initial optimization of those 180 models that we were using on the initial solution. That was somewhere on the order of about 100 hours of total training time, optimization time, data scientists looking at the results, deciding which models to choose, stacking them. So it was a lot of manual work that went into doing that, because we didn't have tools at our disposal at the time to do these type of embedded optimizations to our solutions. Okay, so keep that number in mind. Now, with SigOpt. So there's a few things as a data scientist that I really like and appreciate about SigOpt, and I think are also very valuable when you're talking about using it for these types of competitions. One, and maybe the most important of which, is framework agnostic. So at the time, we were using TensorFlow. More recently, now I'm using PyTorch. SigOpt really doesn't care. So it's very flexible to the type of underlying solution that I want to use under the hood. Very simple to install. I can just pip install it, export, set up my project, and I'm ready and off to go. Now, another thing, when you're working on these competitions or you're working on a real world problem, it's very important to understand, okay, what am I trying to optimize for? If I've got a real customer who cares about latency, how many camera streams per industrial PC am I going to run? How fast does the model need to run? What kind of accuracy do I need to get, and what those trade-offs are? You've got to understand that up front. Here on these competitions where I'm just trying to optimize for accuracy, great. I know what I need to do. So I can set up a very simple configuration file, like over on the right-hand side of this slide, that shows here are the parameters that I'm going to optimize for. So in this case, I'm taking my efficient net B0 model, and I'm optimizing for what I would consider some of the standard hyperparameters. So batch size, learning rate, number of epochs, etc. And then in order to incorporate that into my standard workflow, and a lot of these workflows, as you may know, are relatively standard and repeatable, and we find ones that we like for given tasks, be it classification or anomaly detection or in any such task, I can easily embed it into my workflow by just defining what my parameters are, linking it to this configuration file, and then uh, hooking it into my scheduler. So in this case, for my one cycle learning rate schedule, I've got it hooked now to my SigOpt parameters that are going to be optimized. And then next thing you know, I'm off and running and doing my experiments. I just have to add my SigOpt optimized -e to the beginning of my executable, and I'm off to the races, and that's all I need to do. Now, compare that to the way we initially did this optimization. It was all brute force. It was all in loops. It was random search essentially, so it was very inefficient. Required a lot of computation time, a lot of manual interpretation of the results, exporting a bunch of log files, doing manual work to see where our optimizations really lied. Without a good understanding actually of what parameters drove the optimization, just picking out and cherry picking the models that gave us the best results. So, it's really not much more than black box engineering at that point. But here with SigOpt, in this case, to take this, what's now could be considered the first place solution, 6 lines of code. Okay, 6 lines of code. I can do all of this optimization. Now, when I do that, I also get some things that as a data scientist, I greatly appreciate, which is, visibility into what's going on inside that black box. Which of these hyperparameters really matter? Which ones are turning the knob in terms of what's driving my performance? This helps me as a data scientist to know where I need to focus my model, where I might want to make other changes into my code, where I might want to further sub-optimize a model. Because again, for a challenge where the whole goal is to give accuracy, 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 well, now that I know what's driving that and what's not, I can really define my experiments and hone in on where the most bang for the buck is going to be. So in this particular case, these are some of the visualizations that come out of SigOpt for what's driving my results. And so the parameter importance chart is really important from a first order perspective to look at, to understand what the driver is here. So in this case, it's the starting learning rate as well as batch size. Not too surprisingly, those are generally first order variables that matter quite a bit. In a data set like this, it's actually especially important when you're dealing with a relatively small sample size, only 1,600 images, which could fit into memory and any modern day GPU. So you really want to make sure you understand and optimize for this without overfitting. So understanding what parameters matter the most is highly important. I also like and appreciate how I can kind of walk through and understand what parameters were where to give me a certain accuracy. That's also really important to take out the variables that don't matter most, so I can focus on the ones that do. I'm also, as a data scientist, I like to put my eyeballs on the charts that tell me what drove my results. I'm looking for things like outliers. I'm looking for things like anomaly. Did I get the highest accuracy just because I may have had this weird data point, but all the other data points around it don't really line up to that? So that could be a hint to me that on a small data set size, I could be overfitting to a given problem. So I can get good insight into that by looking at these visualizations that are handed to me. And then I can dissect where I want to go next. From doing this in an automated fashion versus doing all of this manually, I mean, it's impossible to compare the two. Today, I would never spend 100 hours again on a challenge like this when I can go through a much larger sequence of optimization, use a lot less compute power and compute time, use a lot less of my own time as a data scientist, so I can be doing other tasks or working on maybe a second competition at the same time. That's the kind of thing that I want to be spending my time on, where I think the best value or bang for the buck is. So, the punchline here is taking this now more modern architecture and doing the optimization on it. It took about 4.5 hours of total computation time. And that's because this is a relatively smaller data set, compact size with with smaller images. So I can get through all of these optimization runs relatively quickly. So 4.5 hours later, I get a boost in my accuracy of 4%. Now, just to put that, so went from 89.17% accuracy to 91.25% accuracy. Just to put that in perspective, that is about 400 slots on the leaderboard. Okay. There were 3,400 people in this competition. So that's about a 10% jump in your relative ranking on the leaderboard, and took the first place solution. And 4% is absolutely enormous. I mean, that's the difference between ending up at the top and, being in the level with the Grandmasters, or being down to the point where you're not getting any ranking points or moving yourself up, all through an automated workflow and all it takes is a configuration file and 6 lines of code. Okay. As a Kaggle Grandmaster and as somebody who does this all day, every day, sign me up. I'll take this. This is the kind of thing that I want, that makes my job easier and can help boost my results. So a few things in conclusion. So it's important to note here to make sure we're not comparing apples to oranges. Updating the network architecture alone, just from 3 years ago, kind of tells you how fast the whole AI ecosystem has been moving. That's what got us back up to parity with the first place solution. Okay. But just getting up to parity to a previous first place solution is not that interesting. I think we all know that architectures have improved. What's really the point to me here and the value that I see is optimizing that solution so much higher than we could have done just 3 years ago, with only about 4.5 hours of compute time and 6 lines of code. I think that speaks to the value of what was done here. Now, I'll tell you, this is not just something that's useful for competitions. It's illustrative to show, because you've got a lot of data and a lot of people who have worked on the same problem, to see, okay, this is something you can do and understand it in a standard way and compare to other results. But in the real world, what I like here is that not just can I optimize for a single variable like accuracy, I can optimize for multiple variables. And that's so important, because most customers, most people who are trying to solve a real world AI problem are usually dealing with these trade-offs like we talked about: accuracy, latency, speed, performance, maintenance. So being able to optimize for things that are going to influence those variables is really important here. And the fact that you can do it so easily, hook into standard pipelines, be framework agnostic, this is something that I really recommend that people use and explore and try to do on their own. So anyway, so that is my take on what we can do here with a first place Kaggle solution. And I would encourage you to go back and do something similar. Go back and take a solution that you've worked on, that you've established as, with some credible baseline, and do something similar here. Add a few lines of code, add a configuration file, and see what else can you get using SigOpt. My guess is you're going to see something similar to the results that I showed you here today. And if so, I think you'll be able to see the value in it. So thank you very much. It was a pleasure being with you today.